All right, well, this is the last lesson that we're going to have in, actually, for the semester. And it has to do with one other type of acid and base that I want to introduce you to. You might say, why do we need another acid or base? We already have the Lowry acid, the Arrhenius acid, which is a proton donor. If I can put that up here. If we have an Arrhenius acid, that is a proton donor. And a proton, if you remember, is an H+. And an Arrhenius base is a hydroxide donor. And that would be an OH-. And that covers a lot of stuff, but it does not fully describe acids and bases. In fact, we're not going to fully describe them. There's even a deeper definition than what we're going to get to. I mentioned that vinegar is your most common household acid. The most common household base is ammonia, NH4, or NH3. Now, if I drop ammonia into water, something like this happens. The water is actually split apart and breaks up into H+ plus OH-. And the H+ attaches to the ammonia, and that water splits apart and we get an OH-. Now, when you look at that, you say, okay, but this isn't a base. This is an acid-base reaction. But notice what happened to your ammonia. It did not give away an OH. Now, there's an OH that was produced, but that came from the water. So the water, in a sense here, produced the H+. It also produced the OH-. Water, in this case, acted both like an acid and a base. If we had Arrhenius acid being or base, the only thing that we could work with, ammonia is neither of those. It didn't donate a proton, and it did not donate a hydroxide ion. The explanation comes from a pair of scientists who worked together, worked at the same time, I should say, Bronsted-Lowry. And they redid the definition of acid and base. A Bronsted-Lowry acid is a proton donor. Well, that sounds familiar because it is. But a Bronsted-Lowry base is a proton acceptor. Proton acceptor. What that means is that you cannot have an acid without a base, because you can't have something giving it away without something taking it. So in this case, by our definition, NH3, which ended up going over here, accepted an H+. And therefore, NH3 in this particular reaction is a base. H2O is the one that donated, because it ends up over here. So H2O became HOH with the plus, and the plus went to here, and the OH went over to here. In this case, water is an acid. Now, you might say, well, water's neutral. It can't be an acid or a base. Well, it depends on your definition. The definition here, it is an acid because it gave away an H+. If I take hydrochloric acid and I put it into water, a very interesting thing will happen. And that is that this will form a reaction that looks like this, H3O plus CO minus. And by the way, these reactions actually go both directions. And so you're going to see this in your book. It'll be like this. Now, I want you to watch what happened here. This HCl is both an Arrhenius acid and a Bronsted-Lowry acid. It gave away an H+. H+, a proton, is one of the most reactive ions in the universe. H plus will never just float around. It's a tiny positive charge, as tiny as is possible. And this H plus will join with H2O and give you H3O plus. So if I have H2O and I have an H plus and this H plus attaches, look what happens. I have 3 hydrogens, 1 water, and I have a positive 1 charge. This ion is called the hydronium ion. And that's actually fairly important. So OH minus is the hydroxide important ion. This is the hydronium ion. So in this reaction, I want you to see what happens. HCl became chlorine minus. And H2O became H3O plus. How did each happen? HCl lost a chlorine. H2O lost a chlorine, lost the H plus. H2O gained an H plus. I should put it up here. Gained an H plus. And in this reaction then, HCl is our acid and H2O is our base. Notice that the water was an acid in this reaction, it's a base in this reaction. That's because water can either lose an H plus or gain an H plus, and therefore it can fit both definitions. Okay. Now, let me take this reaction. In fact, we'll do both of these. I want to write them both out without all my scribbling on there. This reaction that we start with, NH3 plus H2O, becomes NH4 plus OH minus. But in reality, what happens, this reaction could go both directions. Which means that if I was to look at the reaction this way, okay, so that it was this reacting here, this symbol means that these will break apart and form this, but these recombine to form over here. Well, if in this one, this is the base, because it accepted, and this is an acid. But if I look at this in reverse, where did NH3 come from if we're going this way? Well, this is my acid, and this would be my base. If I had HCl plus H2O, and I got H3O plus Cl minus, H plus lost a proton, donated a proton, so it is my acid. But water then has to be the base. But over here, if I said this reaction now goes this way, how does H3O become H2O? It loses a proton or donates a proton. It would be our acid, and this would be our base. Now, most of the time, these reactions go mostly one direction and just a little bit the other. And what we need to do is first understand what's happening, and then I want to show you something. This acid and this base are linked together. And what we would say is that HCl and Cl minus, HCl is the acid, and this is its conjugate base. This side, it's a base. It's paired up with HCl. The word conjugate's an interesting word. You use it in math. For instance, if I have x plus 2, x minus 2 is called the conjugate. The conjugate, we also use it in language when we conjugate a verb or conjugate things in, especially verbs. But the word conjugate has the idea of something which is linked together. In fact, it's the Latin word for being married. And the idea is that HCl and Cl minus can't really exist apart from each other. They're linked together almost like they're married. On this one, H2O would be the base, and this would be the conjugate acid. All right. Up here, NH3 is the base. Well, where did what happened in H3, it gained a proton, and so this is the base, and we would call this the conjugate acid. And here H2O is the acid, OH minus is the base, this would be the acid and the conjugate base. So you're going to be asked to identify acids and bases, conjugate acids and conjugate bases. And so I want to take you through that real quickly. If you have a reaction that's written out like we do here, let me do one other one. Let's say I had HNO3 plus H2O, and they give you this H3O plus NO3 minus. And that was given. When I look at this, HNO3 turned into NO3. This we would call the acid. This we would call its conjugate base. We usually abbreviate that CB. And if this is the acid, this must be the base, and this must be the conjugate acid. Okay? And that would be how we would mark those, and you'll be asked to do that in the homework. The other thing they'll do is they will give you an acid, like H2SO4, and they'll say this is an acid, what is its conjugate base? Or they'll give you a base, maybe they'll give you Cl minus, and they'll ask what is its conjugate acid? Well, let's do NH3. They'll give you a base like NH3 and ask what is its conjugate acid. Okay, I'm going to make this real simple for you. The way that you go from an acid to its conjugate base is that you donate a proton. Take an H plus away from here. We've got H2SO4, which is a sulfate attached to 2 hydrogen ions. We're going to take one away. What's left? Well, we have HSO4, and because we have a positive and 2 negatives, this would be HSO4 minus. So how do you get to a conjugate base? Subtract H and 1 positive charge. Then how do we go the other way? To go from, this is to go from conjugate, or from acid to conjugate base. And here to go from base to conjugate acid. We're going to do exactly the opposite. You're going to add an H plus. So this would become NH, and I would have 4 of these, and I've added a positive charge. By the way, something like H2SO4, this is going to be a little mind expanding here. H2SO4, when it forms its conjugate, it loses 1 and gets HSO4 with a -1. We just did that. But this, it turns out, is also an acid. It has a hydrogen it can get rid of. And this one can go over here and become SO4 -2. Okay? So if I was to ask, what is this? This is my acid, H2SO4. What's its conjugate base? HSO4 minus. But if I said HSO4 is my minus is my acid, what is its conjugate base? And its conjugate base would be SO4 minus. I don't know if you see it or not, but HSO4, because it sits right here, is, if this is the acid, this is a conjugate base. But if this is the acid, this is the conjugate base. It is both an acid and a base. It could gain a hydrogen or it could lose a hydrogen. So they're going to do a number of questions. I just want to show you a few of them. They're going to give you a pair and ask, is this the conjugate acid for this? So they give HSO4 minus. Well, let me do one from number 7. They give H2SO4, and then they give SO4 minus 2, and they ask, are these conjugate acid-base pairs? No, because this lost 2 hydrogens. they might give you something, like in number 11, they give ClO4 minus, and they say this is the conjugate base, what's its acid? Well, conjugate base, we add a H plus, and we'd have HClO4. So we're going to do page 504. This is our last assignment. We're going to do problems 8 through 16 on page 504. So, and you should probably read through section 15.1. I know that sounds odd. Actually, probably through 15.1 and 15.3. By the way, they're going to mention in there that if this is a strong acid, the base is weak. If this is a strong acid, the base is weak. And it turns out this is the strongest acid there is. So water is an extremely weak acid or base. But that finishes up our section on acids. And with that, we'll quit.